Tonight we are going to explore the most uncomfortable idea in all of science. Uncomfortable in the way that the moment you realize you are being watched, not by someone you know, not by someone benign, but by something whose intentions you cannot read and whose capabilities you cannot assess. That moment of cold, clarifying animal recognition. The idea is this: the universe is not empty. It almost certainly contains other intelligent life. The mathematics of probability, the sheer scale of the cosmos, the chemical universality of the building blocks of life, all of it points in the same direction. We are probably not alone. And the universe is silent, completely, bewilderingly, deafeningly silent. No signals, no megastructures visible in the telescope data, no gravitational anomalies that betray engineering on cosmic scales. No visitors, no responses to the signals we have sent. Nothing. The silence has persisted for decades of searching, and it has deepened with every improvement in our instruments. And it has become, over time, one of the most important unsolved problems in science. The question is not whether the silence is strange. It is. The question is what it means. And the answer that the physicist Enrico Fermi gestured at in 1950, and that the Chinese science fiction writer Liu Cixin developed into a full cosmological theory in 2008, and that a growing number of serious scientists and strategists have begun to take seriously in the years since, is the most terrifying answer available. The universe is silent because the universe is a dark forest. Every civilization in it is a hunter. And the hunters have learned, over whatever length of time it took them to learn it, that the only safe move is to stay quiet, stay hidden, and to kill anything they find before it can kill them. If this theory is correct, and I want to be clear with you tonight that it is not proven, it is not even close to proven, but it is logically coherent in a way that makes dismissal feel irresponsible, then the silence of the universe is not evidence of emptiness. It is evidence of strategy. It is the silence of predators in the dark who have long since stopped announcing themselves. And we, on this pale blue dot, have been screaming into the dark since 1974. Sit with that for a moment before we go any further. We are going to spend the next 2 hours taking this apart completely. The physics, the logic, the specific chain of reasoning that leads from plausible premises to a conclusion that should change how you think about our species and our future. The counter-arguments, the psychological weight of living in a universe where this might be true. And at the end, something that is not quite comfort, but might be the closest thing available, a way of holding this idea that does not crush you. Before we go further, I want to say something directly. Consider subscribing to this channel. It does help this content find more minds like yours, people who stay awake searching for the truth in the dark, rather than the comfort in the light. Now, let us start at the beginning. Not the beginning of the dark forest theory, the beginning of the problem it is trying to solve, the Fermi paradox. In the summer of 1950, Enrico Fermi was having lunch at Los Alamos National Laboratory with a group of colleagues that included Edward Teller and Herbert York. They were talking, as people at Los Alamos in 1950 tended to talk, about many things simultaneously: the news, physics, the mundane texture of the day. The conversation had touched on a recent New Yorker cartoon about flying saucers, and the discussion had drifted, the way conversations at that table tended to drift. toward the serious version of the question the cartoon was poking fun at. Are there other civilizations out there? And then Fermi, who had a habit of performing rapid back-of-envelope calculations that cut through the surface of a question to its mathematical core, said something that no one at the table could adequately answer. He said, "But where is everybody?" That question, 3 words, the most productive 3 words in the history of astrobiology, is called the Fermi paradox. It is not, strictly speaking, a paradox. It is an observation about a discrepancy. The discrepancy between how many civilizations we should expect to exist, given the size and age of the universe, and how many we can actually detect, which is 0. Let us feel the weight of the discrepancy properly. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, a few 100 billion stars. That is, very roughly, a number that looks like this: 2 followed by 23 zeros. Stars. In the observable universe alone. And the observable universe is not all of the universe. It is just the part from which light has had time to reach us in the 13.8 billion years since the Big Bang. The actual universe is almost certainly far larger, possibly infinitely larger. Of those stars, a significant fraction estimates range from about 20% to something close to 100%, depending on what kind of star you are counting have planets. We have confirmed thousands of exoplanets directly, and statistical analysis of the Kepler Space Telescope data suggests that planetary systems are the rule rather than the exception. Rocky planets in the so-called habitable zone, the range of orbital distances where liquid water can exist on the surface, are common, not rare, common. Of those rocky habitable zone planets, some fraction presumably developed life. We know that life appeared on Earth very quickly, by geological standards within a few 100 million years of the planet's surface, cooling enough to be survivable. The specific chemical pathways are still contested, but the speed of abiogenesis on Earth suggests that life, once the conditions are right, is not a miracle. It is a process, perhaps a nearly inevitable one. Of the planets with life, some fraction presumably developed complex life, then intelligent life, then technological life, then interstellar travel, or at least interstellar communication. Even if you are deeply conservative about every one of these fractions, even if you assume that only 1 in a million habitable planets develops life, and only 1 in a million of those develops intelligence, and only 1 in a million of those builds radio telescopes, the numbers still produce thousands of civilizations in our galaxy alone. Thousands. In a galaxy that is 100,000 light years across and 12 billion years old. Let us feel the weight of the discrepancy properly. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, a few 100 billion stars. That is, very roughly, a number that looks like this: 2 followed by 23 zeros. Stars. In the observable universe alone. And the observable universe is not all of the universe. It is just the part from which light has had time to reach us in the 13.8 billion years since the Big Bang. The actual universe is almost certainly far larger, possibly infinitely larger. Of those stars, a significant fraction estimates range from about 20% to something close to 100%, depending on what kind of star you are counting have planets. We have confirmed thousands of exoplanets directly, and statistical analysis of the Kepler Space Telescope data suggests that planetary systems are the rule rather than the exception. Rocky planets in the so-called habitable zone, the range of orbital distances where liquid water can exist on the surface, are common. Not rare, common. Of those rocky habitable zone planets, some fraction presumably developed life. We know that life appeared on Earth very quickly by geological standards within a few 100 million years of the planet's surface, cooling enough to be survivable. The specific chemical pathways are still contested, but the speed of abiogenesis on Earth suggests that life, once the conditions are right, is not a miracle. It is a process, perhaps a nearly inevitable one. Of the planets with life, some fraction presumably developed complex life, then intelligent life, then technological life, then interstellar travel, or at least interstellar communication. Even if you are deeply conservative about every one of these fractions, even if you assume that only 1 in a million habitable planets develops life, and only 1 in a million of those develops intelligence, and only 1 in a million of those builds radio telescopes, the numbers still produce thousands of civilizations in our galaxy alone. Thousands. In a galaxy that is 100,000 light years across and 12 billion years old. The dark force theory is one answer. It is not the only answer. There are dozens of proposed solutions to the Fermi paradox, and we will go through the most serious of them tonight before returning to Lutz Sixen's framework. But the dark forest is the answer that has, over the past 15 years, begun to feel the most consistent with both the physics and the logic of the situation. Let us understand why. The starting point is not alien psychology. It is not speculation about what some extraterrestrial mind might want or fear or value. The starting point is much simpler and much harder to escape. It starts with resources. Every civilization, regardless of its specific biology or chemistry or culture or values, exists in a physical universe governed by the same laws of thermodynamics. Those laws are not negotiable. They apply everywhere, to everything, always. And one of the most fundamental things those laws say is that maintaining order, maintaining the complex, low-entropy structures that constitute a living civilization requires a continuous input of energy. You have to eat. Your civilization has to eat. A civilization of 1 billion people has to eat a lot. A civilization of 1 trillion people, spread across multiple star systems, harnessing the energy of multiple suns, has to eat at an almost incomprehensible rate. Now, the universe contains a finite amount of usable energy. Not a small amount. The energy available in stars and in the mass of matter itself is staggering by any human measure, but finite. And it is being converted by the operation of the second law of thermodynamics, from usable to unusable at a rate that is slow by human standards, but inexorable over cosmological timescales. The stars will burn out. The black holes will eventually evaporate. The universe's supply of usable energy is a depleting resource. And against that background, every civilization that exists is competing, not necessarily consciously, not necessarily aggressively, but structurally, by the simple fact of existing and consuming energy. Every civilization is drawing from the same finite pool, and every civilization that expands reduces what is available for every other. This does not automatically produce conflict. Resources are not evenly distributed. Space is large. For most of cosmological history, civilizations would be so far apart that competition for the same specific resources would be negligible. The universe is not a small apartment where everyone is fighting over the last piece of bread. But here is where the dark forest logic introduces its central and most unsettling move. It is not about resources in the end. It is about uncertainty. And uncertainty is the thing that no amount of goodwill, no amount of careful signaling, no amount of treaty or communication or philosophical evolution can fully eliminate. Let me explain what I mean by uncertainty in this context, because this is the piece that most popular treatments of the dark forest skip over or handle badly. The specific logic here is not hand-waving. It is a chain of deductions, and each link in the chain is difficult to break. Suppose you are a civilization that has survived. You are reading this as a thought experiment in which you occupied the position of whatever alien intelligence has made it far enough to be capable of interstellar communication or travel. You exist. You have survived whatever filters your history contained. And one day, through some detection mechanism, a radio signal, a laser pulse, a gravitational anomaly, a probe discovered in your outer system, you learn that you are not alone. Another intelligence exists somewhere in the galaxy. What do you know about it? Almost nothing. You know it exists. You know approximately where it is. You may be able to infer a few things about its technology level from the nature of the signal. But you know nothing about its intentions, its values, its long-term trajectory, its relationship to scarcity, its response to threat, its internal political structure. You know nothing about the decision-making processes that will govern its behavior toward you over the coming centuries or millennia. And here is the critical point. You cannot find out. Not with certainty. Not with the kind of certainty that would justify trusting your survival to the goodwill of a mind you have never met and cannot fully model. The communications lag alone makes meaningful, two-way dialogue almost impossible. If the other civilization is 100 light years away, a question takes 100 years to arrive, and 100 years for the answer to return. 200 years per exchange. By the time you have had 3 back-and-forth exchanges, 600 years have passed. In 600 years, your civilization will have changed profoundly. Their civilization will have changed profoundly. The entity that sent the first message is not the entity reading the reply. You are negotiating with a moving target, and so are they, and neither of you can track the movement in real time. But even if the communications lag were somehow manageable, even if you could exchange information quickly, the problem would not go away. Because the core uncertainty is not informational, it is ontological. You cannot know what they will become. A civilization that is peaceful and cooperative today might not remain peaceful and cooperative. Not because of some sinister quality in its character, but because civilizations change. Values evolve. Political structures shift. Technologies alter the relationship between what is possible and what is tempting. The civilization that contacted you 1,000 years ago, earnestly and in good faith, committed to peaceful coexistence, might be fundamentally different from the civilization that arrives at your doorstep 1,000 years later. And there is a specific asymmetry in the situation that makes this more than just an abstract worry. Technological development is explosive. We know this from our own history. We know it firsthand. In 1903, we achieved powered flight for the first time. 12 seconds. In 1969, 66 years later, we walked on the moon. In 1945, we had no nuclear weapons. 6 years later, both superpowers had them. In 1969, we had no internet. 20 years later, it was transforming civilization. In 2000, we could not sequence a human genome practically or affordably. 15 years later, it cost less than $1,000 and took a few days. Technological capability, once it gets started, does not advance linearly. It advances exponentially. And the specific danger of exponential growth is that it makes the future radically unpredictable in ways that linear growth does not. If a civilization grows linearly, you can project forward and have some reasonable confidence in where it will be in 500 years. It will be somewhat larger, somewhat more powerful, somewhat more developed than it is today. If a civilization grows exponentially, and we have no reason to think that technological development once initiated is anything other than exponential, then a civilization that seems manageable and non-threatening today might be incomprehensibly powerful in a few centuries. From the perspective of an alien civilization observing us, we went from stone tools to nuclear weapons in about 12,000 years. We went from no space capability to landing on the moon in 66 years. We are currently developing artificial intelligence that appears to be following its own exponential trajectory. To a civilization that has been watching us for 1,000,000 years, a civilization that detected the first signs of our tool use or our fires, we would look in the last 12,000 years like something that had been sleeping for a very long time and had suddenly woken up and started growing very fast. And a civilization watching that growth would have to make a decision. Wait and see, or act. Waiting and seeing carries a specific risk. If you wait and see, and the civilization you are watching turns out to be aggressive or expansionist or simply indifferent to your existence as it consumes resources, you may have waited too long. By the time their capabilities have developed to the point where their intentions are clear, their capabilities may also have developed to the point where you cannot do anything about it. This is the fundamental logic of preemptive action in an environment of uncertainty. It is not alien to us. We understand it from our own history. States have gone to war preemptively throughout human history, not because they had certain knowledge of an enemy's intentions, but because the combination of capability and proximity made waiting feel too dangerous. The mathematics of military strategy has been calculating versions of this trade-off. The balance between the risk of acting when it turns out to have been unnecessary and the risk of waiting when it turns out to have been too late for as long as states have existed. What the dark forest theory argues is that this calculation, applied at the cosmic scale, between civilizations that cannot communicate effectively, cannot fully model each other's intentions, and are watching each other grow at exponential rates, produces a single dominant strategy: silence and preemption. Silence because announcing your presence gives away your location, and your location is the one piece of information that a hostile actor needs to act against you. Preemption, because if you are going to act, acting before the other civilization reaches parity or God-level capability is vastly safer than waiting. The term Lou Cixin uses is dark forest, and the metaphor is precise in a way that repays careful examination. A dark forest at night contains many living things. You know this because you understand biology and ecology. The forest is not empty, but you cannot see them. You cannot hear them, except occasionally and indirectly. They have learned through the long, bloody process of evolution that making noise is dangerous. That movement attracts attention. That attention in an environment where predators exist can be fatal. And so the forest is quiet, not because it is empty, because everything in it has learned that silence is survival. Every organism in the dark forest has two properties that are relevant here. First, it wants to survive. Second, it cannot be fully certain of the intentions of other organisms. These two properties, combined with the presence of other organisms that also have these properties, produce a specific equilibrium. Shoot first. Ask no questions. Leave no evidence. Not out of malice, out of cold, impeccable logic. The alien civilization that detects us does not hate us. It does not envy us. It does not want our resources or our planet or our art or our mathematics. It has simply learned, or its evolutionary and cultural heritage has instilled the understanding that an unknown organism discovered in the dark is a threat that must be eliminated before it can eliminate you. This is the dark forest. And the universe, Liu Cixin argues, is exactly this. Now, I want to hold the theory up to scrutiny before we go further because it deserves scrutiny. It is not bulletproof. There are objections, some of them serious, and I would rather present you with the full picture than a selection of the evidence that supports only one conclusion. The first major objection is what might be called the cooperation counterargument. What? The dark forest assumes that the dominant strategy in an environment of uncertainty is preemption. But game theory, the branch of mathematics that analyzes strategic decision-making, also produces other equilibria. In particular, the iterated prisoner's dilemma, which models what happens when two parties face repeated decisions about whether to cooperate or defect, tends to produce cooperation rather than defection, at least among parties with long-time horizons. The logic is familiar. If you know you will interact with another party repeatedly over a long period, the short-term gains from defecting are outweighed by the long-term costs of losing cooperative opportunities. And civilizations, by definition, have long time horizons. A civilization that has survived long enough to develop interstellar communication has presumably already demonstrated some capacity for long-term planning. So why wouldn't game theory produce cooperation between civilizations rather than the dark forest equilibrium? The answer is in the specific features that distinguish cosmic civilizations from the standard prisoner's dilemma setup. In the standard iterated prisoner's dilemma, both players know they will interact again. The shadow of the future, the expected value of future cooperative opportunities, is what drives cooperative behavior. But between civilizations separated by light years, the shadow of the future is very different. The communications lag means that the strategic situation changes faster than meaningful communication can track. By the time a signal arrives, responds, and the response arrives, centuries have passed. The game has been played and replayed many times without either player being able to update their strategy based on the other's moves. This is a profoundly different situation from the standard iterated game. It is more like a game played by letter, where each letter takes 100 years to arrive and 100 years to return, and the player who sent the first letter has died and been replaced by their great-great-great-grandchildren by the time the reply comes. The repeated nature of the game breaks down entirely, and without the repeated game structure, the dominant strategy shifts dramatically toward defection, or in this context, towards silence and preemption. The second major objection is the technological leap problem. You might argue that a sufficiently advanced civilization, one that has survived for millions of years, and developed technology that is, by our standards, godlike, would not feel threatened by us. We are so far below their capability level that we pose no conceivable threat. Why would they bother eliminating us? This objection has intuitive appeal, but it fails on examination for a specific reason. It assumes that capability gaps remain stable. They do not. We have already established that technological development is exponential. A civilization that is vastly more advanced than us today was presumably once at our level or below it. From that civilization's perspective, looking at us, they are seeing a civilization that has recently undergone explosive development that went from subsistence agriculture to nuclear weapons in 12,000 years. From no space capability to moon landings in 66 years, and is showing no signs of slowing down. From their perspective, we are not a Stone Age tribe. We are a Stone Age tribe that discovered gunpowder last week and is currently experimenting with something that looks a lot like nuclear energy. The relevant question is not what we can do today. It is what we will be able to do in 500 years, or 5,000 years, or 50,000, a civilization that has seen other civilizations develop exponentially. And if it has survived for 1 million years in a populated galaxy, it has seen this happen many times, knows that the window between detectable but manageable and potentially dangerous can be very short. Centuries, perhaps. In cosmological terms, nothing. And so the calculation shifts. Even for a godlike civilization with vastly superior technology, the expected cost of eliminating a young, rapidly developing civilization is low, far lower than the expected cost of letting it continue to develop until it reaches parity or superiority. This is not cruelty, it is arithmetic. The third major objection is the non-aggressive civilization problem. The dark forest logic, you might argue, breaks down if there exist civilizations that are genuinely, philosophically, constitutively committed to non-aggression. Civilizations that have evolved beyond the competitive instincts that drive the dark forest calculus. Maybe the galaxy contains entities that are so far beyond us, so enlightened, so thoroughly liberated from the zero-sum thinking of biological evolution that they would never consider preemption. And maybe those entities would be visible to us, would signal, would help, would create a different kind of cosmic environment than the dark forest. This is the protector of nurseries hypothesis, which some researchers have taken seriously. Maybe advanced civilizations actively shield developing ones. Maybe we are in a protected zone of the galaxy, and the silence around us is not the silence of hunters, but the silence of a wildlife preserve. It is a pleasant idea. It is not without problems. The most serious is that it requires essentially all sufficiently advanced civilizations to have this character, or at least for the ones operating in our region of the galaxy to have it. One exception, one civilization that did not evolve this enlightened stance would be sufficient to make the dark forest real. And we have no particular reason to believe that the evolutionary or cultural pressures that produce intelligent civilizations necessarily produce benevolent ones. We know from our own history that intelligence and benevolence are not the same quality. We are a reasonably intelligent species, and our history includes genocide, ecological devastation, nuclear weapons production, and the current trajectory toward artificial intelligence systems whose alignment with human values we cannot guarantee. Intelligence produces capability. It does not produce goodness. There is one more counter-argument that deserves serious attention, and it is the one that I find most genuinely complicating for the dark forest theory. It is the filtering problem. Liu Cixin's logic produces a dark forest equilibrium by assuming that civilizations faced with uncertainty about other civilizations' intentions will tend toward preemption. But this logic applies symmetrically to every civilization, including our own. If we are the kind of species that, given sufficient capability and sufficient uncertainty about another civilization's intentions, would choose preemption, if that is what intelligence and survival instinct produce, then we are ourselves a dark forest entity. We are one of the hunters. And this is uncomfortable in a specific way, because it means that the dark forest is not something being done to us by alien others. It is something we are participating in. It is the collective result of a survival strategy that we would, if the tables were turned, probably also employ. The dark forest is not a predator and prey relationship. It is a community of predators, each one hunting all the others, each one hiding from all the others, each one knowing that every other entity in the forest is doing exactly the same calculation they are doing. The hunters and the hunted are the same beings. This is in some ways the most psychologically destabilizing aspect of the theory, because it removes the comfort of being the victim of an unjust universe. We are not innocent creatures being threatened by hostile aliens. We are one thread in a web of mutual hostility that arises not from evil, but from the basic logic of self-preservation in an environment of radical uncertainty. Now let us talk about what the silence actually looks like in the data. Because we have been speaking in abstractions, and the Fermi paradox deserves to be grounded in the specific texture of what we have found, and not found in 70 years of searching. The search for extraterrestrial intelligence, SETI, began in earnest in 1960 with Frank Drake's Project Ozma, which pointed a radio telescope at two nearby sun-like stars and listened for signals at the hydrogen line frequency, the 21-centimeter emission line of neutral hydrogen, which was thought to be the most logical frequency for communication because any technological civilization would know about it, and it cuts through the interstellar medium cleanly. Nothing. Drake found nothing. In the decades since, the search has expanded enormously. The frequencies monitored have broadened. The number of target stars has increased from 2 to hundreds of millions. The sensitivity of the instruments has improved by many orders of magnitude. We have listened at radio frequencies, at optical frequencies. We have looked for laser pulses. We have looked for anomalous infrared signatures that would betray Dyson spheres or other megastructures. We have analyzed the spectra of stellar systems for chemical signatures of industrial civilization. Nothing. Well, almost nothing. There was one signal. On August 15th, 1977, a Big Ear radio telescope at Ohio State University, running an automated sky survey, detected a signal at the hydrogen line frequency that was so strong, so consistent with what a genuine extraterrestrial transmission might look like, that the astronomer Jerry Eman, reviewing the computer printout the next day, circled it in red pen and wrote a single word in the margin: wow. The wow signal lasted for exactly 72 seconds, which was the duration of time that Big Ear's fixed beam spent on any given patch of sky as the Earth rotated. It matched the expected signature of an extraterrestrial transmission in almost every detectable parameter. It came from the direction of the constellation Sagittarius. It has never been detected again. In the 47 years since, astronomers have pointed every major radio telescope at that region of sky and found nothing. The WOW signal remains, to this day, the single most intriguing candidate signal in the history of SETI, and it has never been repeated. What do we make of this? If it was a genuine transmission, the silence since 1977 is itself data. A civilization that sent one signal and then stopped. A civilization that is aware that signals can be detected and has chosen not to send more. A civilization that sent one signal before they understood or were reminded what the dark force logic demands. Or the WOW signal was something natural, a comet passing through the beam at the wrong moment, its hydrogen cloud mimicking a directed transmission. This is actually the most commonly accepted current explanation, though it remains contested. Either way, 70 years of serious searching have produced one ambiguous candidate and otherwise total silence. Let us now turn to the specific mechanisms of detection and concealment that the dark forest theory implies, because this is where the theory produces its most testable predictions and its most specific scientific content. If the dark forest is real, if civilizations are hiding and hunting, then we should expect several things to be true about the distribution of detectable signatures in the universe. First, we should expect that any civilization that has survived long enough to become truly powerful has also necessarily developed the capability to conceal itself. A civilization that announced itself in the early stages of its development and was subsequently destroyed would not be here to tell the story. The survivors are the hiders. The ones we might eventually detect, if we ever detect anything, would be the ones that were somehow forced into visibility, the ones that made a mistake, or the ones that decided detection was no longer the greater risk. Second, we should expect that the universe contains evidence not just of life, but of destruction. If civilizations are being eliminated, if the dark force logic is producing preemptive strikes against detected civilizations, then there should be, somewhere in the astronomical record, evidence of these strikes. This is one of the most disturbing predictions of the theory, and also one of the most difficult to test. What would a civilization-ending strike actually look like to an observer thousands of light years away? The physicist Stephen Webb, in his comprehensive treatment of the Fermi paradox, notes that we would not necessarily expect a civilization-ending weapon to be subtle. A sufficiently advanced civilization choosing to eliminate another might use something like a gamma-ray burst, the most energetic events in the observable universe, produced naturally by the collapse of massive stars or the merger of neutron stars, but theoretically also producible by a civilization with sufficient technical capability. Gamma-ray bursts are sterilizers. A gamma ray burst within a few thousand light years of a planet would strip away its ozone layer and irradiate its surface with enough energy to end complex life. They happen. We observe them regularly. They are, in the standard astrophysical account, purely natural phenomena, but we cannot rule out that some of them are not. We cannot rule out that somewhere in our observational catalog of gamma ray bursts, there are events that were not the deaths of stars but the murders of civilizations. We cannot distinguish between them. This is one of the genuinely chilling implications of taking the dark forest seriously. We may be observing evidence of cosmic warfare and interpreting it as astrophysics. Third, the dark forest theory predicts that any civilization that has survived will show specific signatures in its behavior and development that reflect the pressures of the dark forest environment. It will have developed early technologies for concealment. It will have slowed or directed its expansion in ways that minimize detectable signatures. It will have produced cultural and perhaps biological adaptations to the chronic stress of hiding. And it will almost certainly have confronted the same question we are now confronting. Should we ever respond if they received a signal from another civilization, a weak, primitive signal of the kind we have been broadcasting for the past century? What would they do with it? The dark forest answer is clear. They would triangulate, they would assess, they would make a calculation based on the capability level of the transmitting civilization and the expected trajectory of its development. And they would decide, probably fairly quickly, that the safest option was to do nothing, to observe, and to be ready. Now I want to go deeper into the specific mathematics of what Liu Cixin calls the technological explosion, because this is the piece of the theory that gets the least attention in popular treatments, and that is, in my view, the most important. The problem is not just that civilizations develop technology. The problem is the rate at which they develop it and the specific characteristic of that rate. Let me walk you through the numbers. Modern Homo sapiens, anatomically modern humans, have existed for approximately 300,000 years. For the first 290,000 of those years, our technological development was essentially flat. We made stone tools, we controlled fire, we developed language and culture and art. These are not trivial achievements, but they are not exponential. They are slow, incremental, stable. Then, approximately 12,000 years ago, something changed. We developed agriculture. The consequences of this were enormous stable food surpluses, sedentary populations, the possibility of cities, the division of labor, the accumulation of knowledge across generations. And from that moment, the rate of change began to accelerate. Writing appears approximately 5,000 years ago. The printing press in the 15th century, the scientific revolution in the 17th, the industrial revolution in the 18th and 19th, the electrical revolution, the chemical revolution, the nuclear revolution, the digital revolution, the biotechnological revolution, and now the artificial intelligence revolution, all compressed into the last 2 centuries. If you plot human technological capability against time, you do not get a line. You get something that looks flat for most of human history, and then in the last few thousand years, and especially the last few hundred, shoots almost vertically. We are in the vertical part of the curve. And here is what makes this terrifying from the perspective of the dark forest. We do not know where the top of the curve is. We have no good evidence that there is a top of the curve. Every time someone has predicted a plateau, a level of technological development beyond which further progress would be impossible or unnecessary, the prediction has been falsified within a generation or two. The theoretical limits are staggeringly high. The Kardashev scale, proposed by the Soviet astrophysicist Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts. We are currently at about 73% of Type 1. A Type 2 civilization harnesses the full output of its star, about 4 times 10 to the power of 26 watts. A Type 3 civilization harnesses the full output of its galaxy. Between our current level and Type 2 is a difference of approximately 10 billion. Between Type 2 and Type 3 is a difference of roughly 10 billion again. These are not fictional limits. They are the limits set by physics. And we have no theoretical reason to believe that a civilization cannot, given enough time and enough survival, reach Type 3. A Type 3 civilization controls energies on a galactic scale. It can, in principle, do things to stars, to entire stellar populations, to the structure of space-time itself, if the physics permits. From the perspective of a Type 3 civilization looking at us, we are not a threat today. We are barely a smudge in the radio spectrum, a century-old leak of television signals and radar pulses spreading outward at the speed of light in an expanding sphere that has reached perhaps 100 light-years in radius. But we are a smudge that is growing fast. In the terms of the dark forest calculation, the question is not what we are now. It is what we will be in 1,000 years if the current rate of development continues. And the current rate of development is the fastest in human history, with no evidence of slowing. 1,000 years of exponential technological growth from where we currently stand would put us somewhere that is genuinely difficult to predict. We might have artificial general intelligence that exceeds human capability by factors that make the comparison meaningless. We might have nanotechnology capable of self-replication at scale. We might have physics-altering engineering of a kind that our current models of reality do not even have good language for. We might have von Neumann probes colonizing the galaxy, colonizing from the outside, from the perspective of a civilization that has seen this happen before, that has watched other young, rapidly growing civilizations develop from detectable to dangerous in the geological equivalent of an eye blink. We look like a countdown, not a malevolent countdown, not an intentional threat, just a natural process that, if left to run, produces something unpredictable and potentially very powerful very quickly. The question every advanced civilization in the galaxy faces when they detect a signal like ours is whether they should let the countdown run. The dark forest logic says no. And this is where we need to talk about something that most treatments of this subject avoid because it is deeply uncomfortable, which is the specific implications for us right now. We have been broadcasting our location for a century. The first electromagnetic signals that would be detectable outside the solar system, specifically the first high-powered AM radio broadcasts, began propagating outward from Earth at the speed of light in the 1920s. They are currently a sphere approximately 100 light-years in radius, centered on Earth, And within that sphere, our presence is, in principle, detectable. Within 100 light years of Earth, there are approximately 400 sun-like stars and thousands of stars of other types. The current estimate for potentially habitable planets within that radius, based on the known statistics of planetary systems, is several hundred at least. We do not know if any of them have life. We do not know if any of them have technology. But if they do, if there is anything within 100 light years of us that has the capability to detect our radio emissions and the inclination to analyze them, they know we are here. They have known for anywhere from a year to 100 years, depending on their distance from us. We have not been hiding. We have been, from the dark forest perspective, standing in the middle of the woods with a torch and shouting. In 1974, we made it worse. The Arecibo message was a deliberate broadcast, a designed, intentional, powerful transmission aimed at the globular cluster M13, approximately 25,000 light years away. It contained, encoded in binary, information about our mathematics, our biochemistry, our physical form, our solar system, and our technology level. We sent a message explicitly designed to be understood by another intelligence. We sent it to a specific target. The physicists and astronomers who designed and sent the Arecibo message were not naive people. They understood the potential risks. The debate that preceded the message and the debate that has continued since is genuinely serious. And the people on both sides of it are not stupid. Those who favor transmission, who advocate for what is called active SETI or MITI, messaging extraterrestrial intelligence, argue that the dark forest logic is too pessimistic, that the signals we have already broadcast are too weak to be detected at interstellar distances by anything less than a civilization of vastly superior technological capability. That a civilization of vastly superior technological capability, if it had hostile intentions, could have acted already without needing our signals to locate us. That the benefits of contact, the knowledge, the technology, the cultural exchange outweigh the risks. Those who oppose transmission, including Stephen Hawking, who was very public about his position, argue that this calculus is wrong, that even very weak signals might be detectable, that a passive SETI posture, in which we listen but do not broadcast, is the prudent default, that the asymmetry of the risk, the potential downside of attracting hostile attention, vastly exceeds any potential upside of contact, demands caution. Hawking, in his typically direct way, made the comparison to the arrival of Europeans in the Americas and what that meant for the people who were already living there. The encounter between a more technologically advanced civilization and a less technologically advanced one has, in every human historical example, gone badly for the less advanced party. Not always through malice, sometimes through indifference, sometimes through simple economic and military disparity, but badly. There is a moratorium discussion happening at serious levels of the international scientific community about whether we should continue active SETI. It is not publicized. It is not headline news. But it is happening. And it is happening precisely because people who have thought carefully about the dark forest logic cannot dismiss it as readily as they would like to. Now, I want to turn from the external question, the question of what is out there and what it might do to us, to an internal question that the dark forest theory opens up about the nature of civilization itself. Because there is something, the theory implies, about the long-term trajectory of intelligence that is even more disturbing than the hunters in the dark. It implies that survival selects for hiding. Think about what this means over evolutionary and cultural timescales. If the dark forest is real, if civilizations that announce themselves tend to get eliminated, then the civilizations that survive are, by definition, the ones that have learned to hide. They have developed hiding as a core competency. They have built their culture, their technology, their expansion strategy around the imperative of concealment. And they may have been hiding for a very long time. A civilization that has survived in the dark forest for 1,000,000 years is a civilization that has spent 1,000,000 years optimizing for concealment. Every aspect of its behavior, every technology it has developed, every expansion it has undertaken has been shaped by the need to leave no detectable signature. What does that civilization look like from the outside? It looks like nothing. It is invisible, not because it is not there, but because it has become extraordinarily good at not being there from any external perspective. It uses energy in ways that produce no waste heat that would be anomalous. It expands in ways that do not change the macroscopic structure of the galaxy in detectable ways. It communicates through channels we have not discovered. It is to us completely indistinguishable from the empty universe. The universe, in other words, might be full of extremely advanced, extremely capable civilizations that are completely invisible to us, not because they lack the capability to be visible, but because they have spent millions of years developing the capability to be invisible. The silence is not absence. The silence is expertise. This is, in a sense, the most philosophically complete resolution of the Fermi paradox. Not that civilizations are rare, or that they destroy themselves, but that the ones that survive long enough to have a serious presence in the galaxy have all converged on the same strategy because the universe has spent billions of years selecting for it. The winners hide, and we are shouting. Let us now spend some time on what the Chinese science fiction writer who formalized this theory actually said, because Liu Cixin's treatment of the dark forest in his trilogy, The Three-Body Problem, and its sequels, is not just science fiction. It is a serious philosophical exploration of the logic of cosmic civilization, dressed in the clothing of a novel, and it deserves to be examined on its own terms. Liu Cixin grew up in a remote mining town in China during the Cultural Revolution. He was trained as an engineer. He spent most of his adult working life as a computer engineer at a power plant in Shaanxi province. He is not a professional philosopher or a professional scientist. He is a person who spent a lot of time alone, doing technical work, thinking about the big questions. And what he produced in the Three-Body Problem trilogy is one of the most rigorous and unsettling explorations of the Fermi paradox in any medium. The dark forest theory, as he presents it, rests on two axioms and two deductions. The first axiom is that survival is the primary need of civilization. Every civilization, regardless of its specific character, wants to continue to exist. This is not a controversial claim. It is as close to a universal as we can postulate for entities complex enough to be called civilizations. The second axiom is that civilizations continuously grow and expand, but the total matter and energy in the universe remains constant. Resources are finite. Growth in a finite resource environment eventually produces resource competition. The first deduction is the chain of suspicion. Given these two axioms, consider what happens when one civilization detects another. The first civilization cannot know the intentions of the second. They might be benign, they might be hostile. There is no way to determine this with certainty from a distance. The first civilization's continued survival depends on correct threat assessment. An incorrect assessment in the direction of assuming benignity when the other is actually hostile is potentially fatal. An incorrect assessment in the direction of assuming hostility when the other is actually benign results in eliminating a potential ally or resource competitor, neither of which is fatal. The asymmetry of the error costs pushes rational decision-making toward treating unknown civilizations as threats. But wait, the first civilization has to consider something further. Even if the second civilization is benign today, will it remain benign? Can it remain benign as it grows and its resource needs expand? The first civilization cannot know this either. It cannot know the trajectory of the second civilization's development, the internal pressures that might shift its values or its behavior, the technologies it might develop that would alter the strategic balance. So the first civilization is not just uncertain about the second civilization's current intentions, it is uncertain about their future intentions. And the uncertainty compounds over time as both civilizations develop and change. The rational response to compounding uncertainty about a potential threat, when the asymmetry of error costs is weighted toward caution, is to treat the potential threat as a definite threat and act accordingly. The second deduction is the technology explosion, which we have already discussed in detail. The observation that the gap between primitive and godlike technological capability is traversable in a cosmologically short time, making the window for safe intervention against a developing civilization very narrow. These two deductions together produce the dark forest equilibrium. Every civilization that reasons through this logic arrives at the same conclusion. Every civilization that acts on this logic contributes to the silence of the universe. Every civilization that does not act on this logic is eventually detected and eliminated by one that has. The equilibrium is self-enforcing, self-sustaining, and, once established, stable across cosmological timescales. This is the dark forest. Now, I want to address something that I think is important before we move into the final section of tonight's discussion, which is the psychological dimension, how to live with this idea. The dark forest theory is not the only serious explanation for the Fermi paradox, and I have not been presenting it as such, but I want to be explicit about the alternatives and why I think the dark forest remains the most disturbing and the least easily dismissed. The most common alternative is the Great Filter hypothesis, which was articulated in its most influential form by the economist Robin Hanson in 1998. The Great Filter proposes that somewhere on the path from simple chemistry to galactic civilization, there is a filter, a barrier, that almost no civilization gets through. Most paths that begin with life end somewhere before reaching interstellar scale capability. Something kills civilizations, or prevents them from forming, or prevents them from becoming visible. The great filter might be behind us. Abiogenesis, the emergence of life from non-living chemistry, might be extraordinarily rare, even in a universe as large as ours. Or the transition from simple to complex cellular life might be the filter, the emergence of the eukaryotic cell, which took approximately 2 billion years to develop on Earth, might be so unlikely that it has happened only once or a handful of times in the observable universe. If the great filter is behind us, then we are extraordinarily rare. We are among the first and possibly the only complex technological civilizations to emerge. The silence of the universe reflects not the hunters hiding, but the absence of anyone to hunt or be hunted. This is in many ways the psychologically preferable interpretation of the silence. We are special, we are early, we may have the galaxy essentially to ourselves, with the enormous responsibility that entails. But the great filter might also be ahead of us. If the filter is something that kills civilizations after they reach our current level of development, nuclear weapons, climate change, artificial intelligence misalignment, biotechnological catastrophe, something we have not yet imagined, then the silence of the universe reflects the common fate of civilizations like ours. Most of them develop to approximately our point, run into some wall, and fall off. If the filter is ahead of us, the silence is a warning. Hansen's famous observation about the great filter is that the discovery of even simple life elsewhere in the solar system, on Mars, on Europa, in the clouds of Venus, would be extremely bad news, because it would suggest that the development of life is not the filter. The filter would have to be something later in the process, somewhere between where that life is and where we are. The closer we find life to our own level of development, the more confident we can be that whatever filters civilizations out of existence is somewhere close to where we currently are. This is the other nightmare at the heart of astrobiology. Not that we will find advanced civilizations out there, but that we will find primitive life and realize what that implies about our own prospects. The dark forest is different from the great filter in a specific and important way. The great filter is a wall that civilizations fail to cross. The dark forest is a choice that civilizations make, or rather, a choice that the logic of the situation makes for them through the cold mathematics of survival under uncertainty. A great filter kills civilizations. A dark forest teaches them to hide. Both are consistent with the observed silence of the universe. But only one of them produces a universe that is actively hostile to us right now. Let me be direct about what I believe, as much as that word applies to a question that is genuinely scientifically open. I think the dark forest is probably partially true. I think the logic is correct. I think the chain of deductions from the axioms to the equilibrium is valid. I think that in a universe with a significant number of civilizations, the selection pressure toward hiding is real. I also think the dark forest in its pure form may be too extreme. It assumes a uniformity of civilization values and decision-making that may not be warranted. It assumes that every civilization everywhere reasons through the same logic and arrives at the same conclusion. In a universe of potentially billions of civilizations across billions of years, the assumption that every single one has converged on the same strategy seems overconfident. The more likely picture may be a mixed equilibrium, some civilizations hiding some communicating, some cooperating, some predating, and a silence that reflects not universal hunting, but the net effect of many different strategies combined with the enormous distances involved and the sheer difficulty of the signal detection problem. But even a partial dark forest, even a universe where some fraction of detectable civilizations respond to detection with preemptive action, is dangerous enough that the caution advocates are right. Even if the probability is low, the stakes are high enough that prudence demands we take it seriously. And we are not being prudent. We have been broadcasting our location for 100 years. We have sent deliberate, targeted messages. We are currently on a trajectory toward developing AI systems that will, if successful, increase our technological capability by factors that no one can reliably estimate, and which will make us, from the dark forest perspective, much more interesting than we currently are. This is not an argument for paralysis. It is not an argument for despair. It is an argument for taking the question seriously at the level of policy and civilizational strategy, which we are not currently doing. The scientific community that takes METI, active SETI, seriously is a very small fraction of even the scientific community. It receives almost no policy attention. There is no international discussion about Earth's transmission policy in any serious institutional context. We are, as a civilization, operating with no coherent strategy regarding a question that is, on the dark forest hypothesis, the most important strategic question we face. Now, I want to go to the most psychologically significant part of tonight's discussion, because we have been sitting in the logic for a long time, and logic, however sound, requires something to carry it into how we actually live. The question is this: how do you hold the dark forest in your mind without it crushing you? Because it is, when you take it seriously, a heavy thing to carry. The idea that the universe might be populated by civilizations that are hiding from each other, that would eliminate us if they detected us, that are watching or might be watching the expanding sphere of our radio signals with a kind of cold, actuarial attention. The idea that the silence around us might not be empty space but full space, populated by watchers who have decided that the safest response to our existence is to do nothing yet. The idea that we might be in a window, a brief, fragile, possibly closing window, where our signals have not yet reached a civilization capable of acting on them. This is a genuinely heavy thing. And I want to offer not a resolution to it, because there is no resolution, but a reframe. The first reframe is this: the dark forest, if true, is not something being done to us. It is something we are part of. We are not innocent civilians in a war being fought by others. We are, by the logic of the theory, potential participants in exactly the same calculus that threatens us. If we ever detect a signal from another civilization, if we ever have the capability to assess and act on another civilization's existence, we will face exactly the same decision that the dark forest theory describes. Do we act? Do we wait? Do we signal back? And we will make that decision under exactly the same conditions of uncertainty and existential stakes that the theory describes. The dark forest is not something alien civilizations do. It is what intelligent civilizations do, including, potentially, us. This reframe doesn't make it more comfortable, but it makes it more honest. The universe is not divided into predators and prey. It is populated by beings that all face the same fundamental uncertainty, the same asymmetric stakes, the same temptation of preemptive security. We are part of the forest, not the trees. The second reframe is about scale and probability. The nearest stars to our solar system are a few light years away. Our signals traveling at the speed of light have reached a sphere of approximately 100 light years radius. Within that sphere, the number of sun-like stars is in the hundreds, and the number of potentially habitable planets is in the hundreds or low thousands. These are not large numbers cosmologically speaking. The probability that any of these stars hosts a civilization that is both technologically capable enough to detect our signals and sufficiently advanced to have gone through the dark forest reasoning and emerged with preemptive capability is, even by generous estimates, not high. The dark forest is a real risk. It is not a certainty or even a near certainty for our current situation. It is a risk that grows with time as our signals spread, as we develop more visible technologies, as we become more interesting to potential watchers. The window we are in right now may be relatively safe. The danger may grow as we develop. This does not mean we should relax, but it means that the psychological weight of the dark forest does not need to be carried as an immediate present terror. It is a distant light on the horizon that we have time, perhaps, to prepare for. The third reframe is the most important, and it is the one that I think deserves to be the final thought of tonight. The dark forest, if true, is a collective action problem. Every civilization in the dark forest would prefer, if it could trust the others, to cooperate. Not because cooperation is idealistic or naive, but because a universe of cooperating civilizations would be richer, more information-dense, more capable of the kinds of projects that require multiple civilizations working together than a universe of mutual hiding and hunting. The dark forest equilibrium is not an equilibrium that anyone chose. It is an equilibrium that the logic of the situation produced. And like many game-theoretic equilibria, it is a trap, a stable state that is worse for everyone in it than some other achievable state would be, but that no individual actor can escape by acting unilaterally. The question of how to escape the dark forest, how to establish the kind of trust that would allow civilizations to reveal themselves without being destroyed, is one of the deepest and most important questions that any civilization in the forest faces. It may have no answer, or the answer might require a level of coordination and institutional design that is beyond the capability of any individual civilization, and would require, ironically, exactly the kind of communication and trust building that the dark forest makes dangerous. Or the answer might be something we cannot currently imagine, some technological or social or philosophical development that changes the fundamental nature of the trust problem. We do not know. What we do know is that we are currently making the worst possible choice, which is neither the disciplined silence of a civilization that has thought through the logic and chosen to hide, nor the open, transparent communication of a civilization that has somehow solved the trust problem and is signaling its goodwill. We are broadcasting loudly, without coordination, without strategy, without any civilizational level consideration of what we are doing or what it might mean. We are in the dark forest. We have been in it for 100 years, and we are acting as if it is a lit city street on a summer afternoon. This is the thing that the dark forest theory demands we confront. Not the hunters in the dark, not the silence of the stars. Our own carelessness, our own assumption that the universe is benign, our own insufficient attention to the asymmetric stakes of our situation. The universe may be patient. The signals we have sent travel at the speed of light, and the civilizations most capable of acting on them are the ones furthest away, who are also the ones that will receive our signals last. We have time. Probably. But time is precisely what the exponential growth of our technology is consuming. Every year that passes, we become more visible, more interesting, and more capable, and a civilization that was not worth the cost of preemptive action last decade might be worth it next decade. The dark forest does not get less dark as we develop. It gets more dangerous. And if we are going to navigate it, if we are going to survive long enough to understand the silence, and perhaps someday to do something about it, we will need to take it seriously. Starting now. Starting with the acknowledgement that the silence is not evidence of absence, that the Fermi paradox is not resolved, that the most important strategic question our civilization faces might not be climate change or artificial intelligence or nuclear proliferation. Though all of those are real, it might be the question of whether anyone is listening and what they are planning to do about what they hear. Let us go even deeper into that carelessness. Because I want to be fair to the people who designed and sent the Arecibo message. I want to be fair to the scientists who argue for active SETI. They are not fools. They are not reckless in the ordinary sense. They are operating from a set of assumptions about the universe that is coherent, internally consistent, and in the most optimistic reading of the evidence, possibly correct. Their assumptions go something like this. Any civilization advanced enough to receive our signals and act on them is also advanced enough to have long since moved beyond the resource competition logic that drives dark forest reasoning. A civilization that has harnessed the full output of its star, a Type 2 civilization on the Kardashev scale, does not need our planet. It does not need our resources. It has access to energy on a scale that makes everything Earth has to offer completely irrelevant. What would they want from us? What could we possibly have that they could not produce 1,000 times over from the raw material of their own solar system? This is a serious argument, and the people who make it are not naive about what it implies. They are saying, essentially, that the dark forest logic breaks down at sufficient levels of technological development, that the resource competition which drives the suspicion chain is not permanent, that civilizations grow past it. The problem is that this argument assumes something specific about the developmental trajectory of civilizations that we have absolutely no evidence for. It assumes that as civilizations become more capable, they also become more benign. It assumes that intelligence at sufficient scale and development converges on something like wisdom, on something like restraint, on something like the principled choice to leave other civilizations alone. But we have only one example of a civilization, us. And our trajectory does not show clear evidence of convergence on benignity as capability increases. We have in the last century developed technologies capable of ending our own civilization many times over. We have used 2 of them in anger. We have come within minutes of accidentally triggering the rest of them on several occasions that we know about, and probably others that we do not. Our capability has grown exponentially. Our wisdom has grown, at best, arithmetically. There is no law of physics that says these curves will ever intersect. There is no theorem in any branch of science that says sufficiently advanced civilizations become safe. It is a hope, a very human hope, but it is not a deduction. And the dark forest does not care about hopes. Now I want to spend time on something that is usually treated as a side note in discussions of the Fermi paradox, but that I think deserves much more weight. The sheer age of the universe. We talk about the Fermi paradox as if it is a contemporary problem, as if the universe has been, roughly speaking, available for civilizations to develop in for about as long as our civilization has been around. As if the silence we observe is a silence of the present, a snapshot of current conditions. It is not. The observable universe is 13.8 billion years old. Our solar system is 4.6 billion years old. Life on Earth has existed for approximately 3.8 billion years. Complex animal life for about 600 million years. Humans in our anatomically modern form for about 300,000 years. Technological civilization in any meaningful sense for about 12,000 years now. The universe was capable of producing stars and planetary systems similar to our own within the first billion years. There are stars in our galaxy that are 10, 11, 12 billion years old. There are planetary systems orbiting those stars that formed when the universe was only a few billion years old. If life can develop on a rocky planet orbiting a stable star, and we have good reasons to think this is not a uniquely Earth-specific process, then there are potentially planetary systems in our galaxy where life has had 12 billion years to develop. 12 billion years. We went from simple chemistry to radio telescopes in 3.8 billion years, with most of that time spent as single-celled organisms. If the same process happened elsewhere 8 billion years earlier and followed a roughly similar trajectory, the resulting civilization had 8 billion more years than we did to develop. We cannot imagine what 8 billion years of technological development looks like. We cannot even begin to imagine it. Our entire written history is 5,000 years. Our entire technological civilization is 12,000 years. 8 billion years is 666,000 times longer than our entire technological history. A civilization with that kind of head start is not operating in the same conceptual universe as we are. It is not playing the same game. It is not constrained by the same physics or the same thermodynamics or even potentially the same relationship to space and time that we have. From our perspective, such a civilization would be indistinguishable from the laws of nature themselves. And yet, We did not grow up in a neutral universe. We grew up inside a system that had been running for billions of years before we arrived. It should be untraceable. The attacked civilization should not. because civilizational strategy requires thinking about low probability, high consequence events, not obsessing over them, not being This is a gap, a serious one, and Not because the universe is malevolent, because the universe is indifferent. It does not arrange itself around human desires or human values. It operates. But we are also simultaneously sending much more powerful signals in more concentrated directions. Military radar systems, particularly the Earth. Within that radius, there are millions of stars and potentially tens of millions. The first is that there is We apply it in other domains. We do not run nuclear reactors without containment structures, on the grounds that the probability of a meltdown is low. We do not Who makes that decision? On what basis? With what institutional backing? With what inner The universe is a competition. And we are in it. We are taking the test right now. The carelessness That is not nothing. In fact, for a species that has been around for 300,000 years and technologically capable for 12,000 and cosmically aware for maybe a century,